Okay, so this lesson today is, we're talking about infinite limits of rational functions. And first of all, let's talk about what a rational function is. If we talk about rational, the root word there is ratio. So we're talking about a ratio, which includes sort of a numerator up top and a denominator on the bottom. That's what a ratio is. And comprising that ratio would be two functions. Okay? So you have a function on top and a function on the bottom. And that's what a rational function looks like. In its entirety, it's a function that is created by a ratio of two other functions. Okay. So the infinite limit part of it is, of course, this part. I'm just going to try and erase this. Oh, maybe it doesn't want to. Oh, there we go. But I missed something here. Put that there. So the infinite limit part is basically saying this. What is the limit of this rational function? That is, what sort of y value does this approach when n is taken to infinity? If n approaches infinity. So if this n value that's here, here, and here, if it gets larger and larger and larger and larger, is there a value that, like a y value, that this function would approach? So if we're taking a look at any function, and I don't know what this one exactly looks like right now, but a function that where n or x or whatever the input value approaches infinity is where down here, let's say this is n, it's approaching infinity. It's getting larger and larger and larger. Now, if this value seems to kind of decrease, but then kind of starts to slow down in its decrease, it might be approaching some y value, and this, we've called this in other math classes the horizontal asymptote, right? So it's sort of, what is this boundary line that a function might be approaching? So that's what we're asking. If n was 100, what would this value be? Then compare that to if n was 1,000, what would the value be? If n was then 1,000,000, then if n was 1,000,000,000, then if n was 1,000,000,000,000. Like if you keep going on as it gets larger and larger, there may be one single number that those values seem to get closer and closer and closer to. Now, if the function is such that maybe it doesn't look like this over here, so maybe it doesn't look like this, maybe there's no limit, then it would be a function that appears to increase without any boundary. So it would be maybe something like this, right? As n gets bigger, this graph seems to go higher and higher and higher. So then there's no limit. But how do we know? How do we find out? There's a bit of a trick here, okay? Because of this fact. So here is sort of a rule that we know, okay? The limit of n approaches infinity of 1 over n, really to any power r, but let's just say 1 over n. What happens here to this graph right here as n approaches infinity? Now, if n was 1, the value would be 1. If n was 100, the value would be 1/100. If n was 1,000,000, the value would be 1,000,000, right? So what do those values, as n gets larger and larger, what do those values seem to get closer and closer to? They get smaller and smaller until they start to almost touch or almost reach what value? 0. Very good. So this limit is 0. And that is a rule. Okay? Now, if we can use this rule in simplifying this, and really that's what we're doing, we're going to use the rules of limits, the properties of limits, to kind of simplify this and to apply this limit to each individual term, and then we're going to be able to find our answer here, okay? Because if you plug a billion in here, it might be kind of tough to know what's going on, right? What's a billion squared minus a billion? Oh, divided by 2 times a billion squared plus 1. Like, I mean, it's like, what? So how can we simplify that? And plus, a billion isn't anywhere near infinity anyways, right? Like, really, it's a big number, but it's nowhere near. Okay, so what we're going to do is we're going to try and simplify each term in the numerator and denominator. And we're going to divide the top and the bottom, and that is each individual term. You could do it like that. We're going to divide by the largest degree of n or of the variable that we see in the question. And so if you divide every single term, in this case by n squared, okay, we aren't changing what this function really is, right? We're just changing how it looks. And so if I can rewrite that down here, okay, it looks like this. It comes like this. The limit as n approaches infinity of n squared over n squared minus n over n squared divided by 2n squared over n squared plus 1 over n squared. Yeah, no problem. So the properties of limits, say, and we didn't spend a whole lot of time on the properties of limits yet with you guys, but if you have this situation, you can take the limit of this term and take the limit of this term and of this one and of this one and write it like this. The limit as n approaches infinity, this is going to get long, so let me just speed this up. So once you apply this, you notice that the limit is applied to each term. And of course, this is n squared over n squared, so we can actually simplify that at any point before we applied the limit or after. Apply that to 1. Okay? And that's actually 1. What is this one down here? 2. Okay? That actually is just 2. This one here can be simplified to 1 over n. And this is already kind of 1 over n squared. That's fine. Okay? Now, the important thing to note here from this, and remember I said that really this is to the power of any power where r is greater than 0, I guess. R has to be greater than 0. But, you see we have it right here. See that? See that? So, this is going to approach 0. And this is going to approach 0, but quicker because it's squared. So this is also going to approach 0. Now, what happens to these guys? Well, because this is simplified here, and do you notice that as n changes, how is 1 going to change? Like, what is n going to do to the number 1? If n gets larger, what happens to 1? Nothing. You're exactly right. As n gets larger, the constant 1 doesn't change. It doesn't matter. It doesn't affect 1. So guess what? This is how we're going to simplify this down here. The limit as n approaches infinity of 1 is 1. Minus, we said this was 0. The limit as n approaches infinity of 2, well, n doesn't affect 2, so it stays as 2 plus 0. So guess what? Simplify that. The limit is 1/2. The limit is 1/2. So what I'm going to do now is I'm going to put this on the graphing calculator, and we're actually going to graph it, and we're going to see when x is really large what the graph kind of looks like, okay? All right, so if we put that into the graphing calculator, we have, make sure you use your brackets, so x squared minus x divided by 2x squared plus 1. Of course, that's the same as n, so your calculator can be, that's just the input variable. I changed my window to look like this. So the setting, this is the setting that I have. And when I graph it, here's the function right there. Okay, it's already been mapped here for me. But this is it right here, this line right here. And notice if you look real close, it appears to be getting pretty flat, right? So it looks like it's approaching a limit. And if I change my window one more time to make y max there, let's make that 2. Then this is what the graph looks like. A little stutter right there around 1. But then, okay, so this is 1, and this appears to be pretty close to 1/2, which is what we calculated our limit to over here, see? How can you check that? The second function, calculate the value. Now I'm going to 1,000 here, so let's put 950 in there. And that should be pretty close to value. So just do second function trace there, and then enter, and I put in 950, and enter, and look at that. The y value is 0.4999, so just under 0.5. Okay, so of course if that's close to 1,000. If it was close to 1 billion, it would be even closer to 0.5, if that's even possible. If it was 1 trillion, you see? So the limit itself, now remember limits, as n approaches infinity, there is no infinity, right? So it just means it's getting larger and larger and larger. And if this was allowed to go to infinity over here, then this limit would then be equal to 1/2. With any measurable value that we plug into the calculator, you're not going to get exactly 0.5. Just like we did here, it's 0.499. Now, if I stretch this out and made it a million, which I don't think your calculator would do, there would be some point where 0.4 and then, if there was 100 nines after that, like your calculator is going to write it's going to say 0.5 because it's actually saying, okay, listen, buddy, that x is getting pretty close to infinity, and I think that's really what you mean. I'm not going to write 1700 nines here. You know what I mean? So yeah, so that's how we calculate that. But the little trick is this, very important here. This is the little trick. You need to simplify the rational function by dividing both the top and the bottom by the largest value, the largest degree of the variable that you see in any of the expressions. Okay? So divide each term by the largest value of the variable, and then apply your limit to each term. Use this important, very important rule right here in the red box, and then you should be able to simplify down to find a limit if one exists. Good? Awesome.
So we're just